Hi, I'm Avi.
And I'm Ian.
And this is Lab 9 Shack Cube Interferometer. A Shack Cube interferometer interferes the beam from a test surface with the reference beam from a curved reference surface. To align this specific Shack Cube configuration, the surface under test should focus on the back surface of the beam splitter. This is a popular interferometer choice because the test and reference beams share a lot of the same path. Another benefit is that the Shack Cube measures wavefront error directly and not wavefront error difference like a shear plate. In the first part of this lab, we simulated a Shack Cube using Zemax non-sequential. This allowed us to gain an intuition for what the interferograms for different aberrations looked like. To build the Shack Cube, we first modeled a collimated light source, then added a beam splitter made of 2 prisms. Onto the beam splitter, we added the curved reference surface. The surface had 2.36 millimeters of sag and negative 22.36 millimeters radius of curvature. With the reference surface defined, we added a test surface to form interference patterns at the detector. If the mirror is aberration-free and aligned perfectly, the interference pattern will be a null fringe, meaning there is no OPD change over the entire interferogram. We can add defocus to the model by shifting the position of the test mirror. Adding defocus adds concentric fringes whose spacing decreases quadratically. Increasing defocus increases the number of fringes. Zooming in on interferogram C, by counting the number of fringe pairs radially, we can determine the number of waves of defocus present. There were about 7 fringe pairs, so 7 waves of defocus are present. To add tilt, we can rotate the test mirror. Adding tilt adds straight, equally spaced fringes. The number of fringes increases as tilt increases. Tilting about a different axis changes the fringe orientation, but the behavior is the same. Adding tilt to defocus shifts the central fringe in the tilt direction. We can simulate spherical aberration in the system by changing the mirror from spherical to elliptical and varying the conic constant. Spherical aberration forms concentric rings like defocus, but the spacing changes to the 4th power. To find the amount of spherical aberration in the interferogram, we can count the radial fringe pairs again like we did with defocus. This interferogram has about 6.5 waves of spherical aberration. Adding tilt to spherical aberration moves the central fringe along the axis of the tilt. Tilt plus spherical looks slightly different from tilt plus defocus because spherical is higher order than defocus. The tilt appears to warp the central fringes. The central fringes also shift in the opposite direction. Finally, we simulated all 3 aberrations at once. You can see here that defocus in different directions did not produce mirrored interferograms. With the addition of defocus, we see more or less warping in interferograms H1 and H2 than in interferogram G. To set up the physical Shack Cube, we first aligned a laser through a spatial filter. Then we aligned a long focal length mirror until we saw fringes. Once we found fringes, we attempted to find the null fringe. Unfortunately, we had the bad interferometer, and residual fringes overpowered the fringes we cared about. After 2 hours of attempting to find the null, we switched interferometers.
With the new interferometer, we were able to find the null. Here are results for the null. There were still some residual fringes from ghost reflections from the Shack Cube, but way better than the first interferometer. We then introduced different combinations of defocus and tilt to the test mirror and observed the interference behavior for both a long and short focal length mirror. Here are the results for defocus, tilt, and combined defocus and tilt. In all cases, the fringes are less clean in the real setup, but demonstrate the same behavior. It was harder to get tilt to be purely in X or Y in real life, and sometimes defocus added some tilt from slight misalignments. We chose an interferogram with defocus and tilt to analyze. First, we defined axes across X and P. Then we counted the number of fringes across both axes. Finally, we measured the spacing of each fringe and normalized it so the aberrations will be in terms of waves. Now we can curve fit a 4th-order polynomial. From the coefficients of the fitted polynomial, we can find how much of each aberration is in our system. For example, spherical aberration is the only 4th-order aberration, so the amount of spherical is the average of the 4th-order term from X and P. Here are results. We have the expected amount of defocus, about -7 waves, and tilt, about -3 waves. However, there are a lot of aberrations we do not expect that are significant as well, like 7 waves of astigmatism. This is likely from errors in position from determining spacing by eye and using an interferogram with low fringe contrast. To mitigate these errors in the future, we can try to increase the fringe contrast by using a filter, and we can use a program to count the fringes instead of measuring them by hand.